Hello. If you are into RF engineering, wireless system, or just obsessed with antennas like I am, today's video will be very helpful for you. So in this video, we are diving into ultra-wideband antennas, like what is UWB, basics of UWB antennas, and what has to be the things considered while designing the UWB antennas, and some of the applications of UWB antenna. Okay, let's start with some basics of ultra-wideband. According to Federal Communication Commission, an antenna is defined as ultra-wideband if its fractional bandwidth is more than 20% or if it has a bandwidth of 500 megahertz. So if any of these conditions satisfies, we can say an antenna is ultra-wideband. In most of the cases, the ultra-wideband works from the frequency from 3.1 to 10.6 gigahertz. So I would like to explain a little bit about these frequency power spectral density variation versus the frequency. So here you can see that different applications for different frequencies and how the power spectral density is varying. And this is the power spectral limit for the FCC, and this is the noise floor. So here you can see that UWB spectrum is extending from 3.1 to 10.6 gigahertz, and as compared to power of other applications, the UWB power spectrum is very low and it is just above the noise floor. That means that UWB system is transmitting the power in a very low power level. And another thing is, for ultra-wideband, short pulses with width of nanoseconds are transmitted. So let's see how we can understand this. Why these short pulses come into the effect. So for that, I am going to use this FFT scenario. So this blue color is the time domain and red color is the frequency domain. So we know that if you use the FFT, we can convert the time domain into the frequency domain. So in time domain, we can see how the pulse is varying with the time. That means that at 0 second, how the pulse will look, and at 1 second, how the pulse will look. These type of phenomenon can be seen in the time domain. In frequency domain, it will show how many frequency components are with respect to the frequency. That is the frequency domain. So this blue pictures represents the time domain and these red ones are the corresponding frequency domain plots. So here you can see that we have a very narrow pulse in the time domain. So if we convert that into the frequency domain, you can see that it consists of lots of frequency components from -50 to 50 hertz. So why this negative is, it is because in FFT, when we take the FFT, we will be getting the information about the negative frequency also. That's why we have the axis in the negative axis also. So here you can see that if we have a very narrow pulse, here you can see that in time domain the pulse width is very less, but when you consider the frequency domain, you can see lots of components in frequency. So here I'm just increasing the pulse width in time domain. So here you can see that how the frequency components are getting reduced. So when I increase the pulse width, so here it is in the time domain. So when I increase the pulse width, you can see that the number of frequency components is very less. That means that if we have a very narrow pulse in the time domain, it will contain lots of frequencies. So if the pulse is very wide in the time domain, it will contain very less frequency components. So in case of ultra wideband, we know that it contains lots of frequencies from 3.1 to 10.6. So these frequencies has to be included when we are transmitting a pulse. That's why. So it will be corresponding to these scenarios. So if we have to include lots of frequencies, we have to transmit a very narrow pulse. So that's why we are going to transmit short pulses with width of nanosecond. That's why this is important in ultra wideband. So I hope you get some idea about all these things. So these are the properties of ultra wideband. These are the basic concepts. Let's continue the properties. So first one is we have discussed this short pulses with width of nanoseconds are transmitted, and second one is high data rate. So let's see how the high data rate is formed. So it is based on Shannon-Hartley law. Based on that, maximum error-free data rate of a channel can be given by the expression B log 2 of 1 plus NSNR, where B is the bandwidth. So in case of the UWB, we know that it has a very high bandwidth, and because of that, we can see that this capacity will be increased. That is why it has high data rate. And next one is it is resistant to multipath because we are using very narrow pulse. So because we are using very narrow pulse, as it is getting transmitted, it is very reluctant to the multipath. When it is getting hit on other obstacles like walls and any other things, the multipath effect will be very reduced as we are using very narrow pulse. If we are using a very wide pulse, this will be getting spread out and the multipath effect will be more. So here in this case, even if it is there multiple reflection, the distortions happening on the narrow pulse will be very less. That is, it is known as resistance to multipath. And it can also be used for the ranging application. It also hold for very narrow pulse. As we are transmitting very narrow pulse, we can use for the ranging application. That is, it can be used for uh, like a radar application to find the distance to the object. So when this pulse is getting transmitted, it will hit on this object and it will come back. As it is a narrow pulse, it is very easy to calculate the range precisely, because if it is a very wide band, these type of small objects will not be able to get detected because it will be covering by the wide pulses. So if it is a narrow pulse, even the small distances or small object can easily be get detected. That is one of the other factor. And it is like interference less technology that will attribute due to this power spectral density. Here you can see that the power spectrum of the UWB is very less as compared to other applications. Because of this less power spectral density, it is not providing any interference to other technologies like GPS, Bluetooth, Wi-Fi, etc. And it also has high penetration because its frequency range from 3.1 to 10.6 gigahertz. So at lower frequency it has higher wavelength, and the wavelength is proportional to the penetration depth. That means that at this low frequency can easily penetrate through the walls and other obstacles. So it can be used for short range non line of sight communication. Next, let's see what are the important things to be considered while designing an ultra wideband antenna. So one of the important thing is impedance matching, because we know that it has to match from 3.1 to 10.6 gigahertz. So we have to do some modifications on these feed lines or the ground to obtain this wide bandwidth. So some of the technique can be like tapered feed lines or beveled edges, ground plane modifications like use of defected ground structures, slot loading, or partial ground planes. So these are some of the techniques that can be used to obtain the ultra wideband impedance matching. Another characteristics we have to consider is group delay. So let's see what is mean by group delay. So this is the definition. Group delay is the time it takes for a specific frequency component to travel through a system. So the system can be like a transmission line or anything. That means that Let's see our ultra wideband scenario. So we know that in ultra wideband we have loads of frequency components from 3.1 to 10.6 gigahertz. So let's consider this scenario. So it means that if these frequencies are transmitting through a transmission line, so it is going to a transmission line, uh, the group delay is actually defined as, sorry, this is the group delay. It is defined as the time take for the specific frequency to travel through a system. So this means that all the frequencies has to um, obey the same delay. Like if this frequency is traveling through the transmission line at 2 nanosecond, this frequency component should also travel through that. So the group delay actually defines the speed or time taken for these frequency components to travel through the transmission line. So let's consider it based on an analogy. So let's consider a group of marathon runners are running through a tunnel, and all the marathon runners are coming out of the tunnel at the same time. So we can see that there is no delay. But let's assume that all these runners are coming at different times. Like this one man comes out of the tunnel at 5 seconds, and maybe this woman comes out of the tunnel after 20 seconds. We can say that it is like a spread of these people, right? So the same will apply for our frequency also. So in case of the UWB communication, as we have the wider bandwidth, we have to transfer only short pulse. So all the frequency component must experience the same time delay. That means that all the frequency components will have the same group delay. This means that the phase must be linear with frequency. That is, this is the definition of the group delay. That means that minus d phi by d omega. So the phase has to be linear. So similar to the marathon runners, as the all the marathon runners has to come out of the tunnel at the same time, like taking the same time, the frequency component also has to observe the same phase delay, not phase delay, same time delay experiences. So if the group delay is not flat, that means that some frequencies arrive late. So similar to the marathon runners. So if the people coming at this position are delayed, it is like it is dispersed, right? So the pulse smears out in time. So the our narrow pulse will get smears out. So this will cause ranging errors because it will no longer be a narrow pulse, and it can cause the ranging errors and the pulse distortion and high bit error rates. So these are the some of the issues with the if there is a group delay variation. So for the UWB application, all the frequencies should take the same time to travel through the system. So the group delay has to be constant. That means that if group delay must be constant, if different frequencies within the pulse travels at different speed, the pulse spread out and data or ranging accuracy gets trashed. That's what we explained. Next is radiation pattern stability. This means that throughout the frequency range from 3.1 to 10.6 gigahertz, it should have the same pattern like omnidirectional or something. And it has to be have the compact size because we have to integrate these antennas to some application. It has to be have the compact size, and it should have high radiation efficiency also. Okay, so now we have seen group delay, and these are some of the wideband antenna examples. So planar monopoles, slot antennas, Vivaldi antennas, and printed UWB antennas will act as the ultra wideband antennas. Let's see some of the applications of ultra-wideband antennas because we have seen that we are using the narrow pulse. It can be used for detecting the range for other objects. It has lots of application, and some of the applications are indoor positioning system. So it can be having centimeter level accuracy to detect the object, and it can also used for asset tracking and smart factories. And another thing is consumer electronics. You may have seen these AirTag, and you may have used these AirTags to track the objects. So this is also used for device to device ranging and precision finding. And another one is automotive applications. So it can used for secure keyless entry, short range radar, and collision avoidance. One of the other application is ground penetrating radar, imaging, defense system, and biomedical sensing. It is also used for industrial IoT like real-time location system and warehouse automations. So I hope you get some idea about what is mean by ultra wideband and how what are the things to be taken care while designing the ultra wideband antennas and some of the applications. Thank you.